Welcome to Ultimate Sleep Doctor. Tonight, we'll journey into a realm of ancient mysteries. Let's consider the immense wonder of the pyramids, colossal structures built millennia ago, testaments to a sophisticated understanding of the earth and sky. These towering forms whisper secrets of astronomy, mathematics, and perhaps something beyond our current grasp. They represent a connection to the rhythms of time, a silent dialogue with the stars. As we contemplate their enduring presence, perhaps we can find a gentle resonance within ourselves. If you enjoy exploring the fascinating intersection of science and serenity, please subscribe and share this channel with anyone seeking calm discovery. Let's begin to unwind. Just breathe and let your thoughts drift. Just breathe and let your thoughts wander with me through the quiet science of sleep. The air on the Giza Plateau held a particular stillness, a quiet born of millennia. It wasn't the absence of sound. Of course, the wind whispered across the sand. The sun beat down with relentless warmth, and the occasional cries of birds echoed across the vast expanse. But it was a stillness punctuated by a deeper, more methodical hum, the work of the Geological Survey, begun in the mid-19th century, a dedicated effort to unravel the secrets of how the Great Pyramids had been built. Before modern techniques like radar and ground-penetrating imaging, the survey, led by figures like William Matthew Flinders Petrie and, later, Edward Roy Anderson, relied on careful observation, meticulous measurement, and a growing understanding of the stone itself. The core of the survey's work revolved around identifying the quarries from which the limestone, granite, and basalt used in the pyramids originated. It quickly became apparent that the blocks weren't all from one single location. The sheer scale of the project demanded a diverse supply chain, and the geological variations within a relatively small area, the Giza Plateau itself, necessitated a network of carefully managed sources. The most abundant material, by far, was the Tura limestone, a fine-grained, white stone quarried from Tura, a small outcrop just to the east of the pyramid complex. This limestone formed the bulk of the Great Pyramid's outer casing, the remarkably smooth surface that reflected the sunlight and gave the structure its iconic appearance. Analyzing the Tura limestone revealed a unique composition, richer in calcite than many other limestone deposits, which suggested a specific aesthetic choice by the pyramid builders. They prioritized a stone with a particularly bright, reflective quality. Moving further afield, the core blocks of the Great Pyramid, the massive stones that formed its internal chambers and passageways, were primarily extracted from quarries located to the west of the plateau. The principal source here was the Gizan limestone, found in several locations, but most notably, the quarry known as the Big Roman Quarry, so named by the British after their occupation of Egypt. This quarry produced blocks of a slightly coarser, heavier limestone, perfectly suited for supporting the immense weight of the structure. The survey teams painstakingly mapped the geological layers within this quarry, documenting the presence of different rock types and the techniques used to expose the stone. They discovered that the ancient Egyptians didn't simply hack away at the rock face with brute force. Instead, they employed a sophisticated system of levers, ramps, and wooden wedges. The quarrying process began with carefully chosen points of weakness in the rock face. These weak points were identified through a combination of observation, noting areas where the rock was fractured or where the surface was slightly softer, and, surprisingly, a rudimentary understanding of hydraulic pressure. The Egyptians used water to create controlled fractures. Wooden wedges, bored with holes, and then packed tightly with water, were hammered into these fissures. As the water was withdrawn, the wood contracted, exerting immense pressure that split the stone along predetermined lines. This wasn't a random, destructive process. It was a controlled, precision operation. The survey documented the precise angles of these fractures, indicating the skill and understanding of the quarrymen. Beyond limestone, the pyramids incorporated significant quantities of granite, a much harder and more challenging stone to work with. The iconic, shimmering black blocks found in the king's chamber and elsewhere came from Aswan, a city located over 800 kilometers to the south. Transporting this stone across the desert was an astonishing feat of engineering. The Egyptians likely used a combination of barges transported by the Nile River during the annual flood season and overland transport by sledges, pulled by teams of oxen. The survey revealed evidence of carefully constructed roadways leading from the Nile to the pyramid site, and even found traces of the wooden rollers and sledges used to move the heavy blocks. Basalt, a dark, volcanic rock, was used for paving, drainage channels, and some internal elements. The basalt quarries were located at Abu Rawash, a site about 30 kilometers north of Giza. The survey found evidence of basalt being shaped using hammers and chisels, a testament to the Egyptians' skill in working with materials that were far more difficult to manipulate than limestone. The survey's detailed mapping of these quarries, coupled with the analysis of the tools and techniques used, built a surprisingly complete picture of the logistical challenges and engineering prowess involved in constructing the pyramids. The survey wasn't simply about identifying the sources of the stone. It was about understanding how the Egyptians worked with it. The careful placement of tool marks, the patterns of fractures in the stone, and the alignment of quarries all suggested a deep, practical knowledge of stone properties and a commitment to efficient, controlled methods. It revealed that the pyramids weren't built by a disorganized mob, but by a highly organized workforce employing sophisticated techniques. The meticulous documentation produced by the Geological Survey remains a cornerstone of our understanding of these magnificent structures, a silent testament to the ingenuity and determination of the ancient Egyptians. The quiet stillness of the Giza Plateau wasn't empty. It held the echoes of a powerful, deliberate process, a story whispered through stone. The Giza Plateau wasn't just a collection of rock. It was intrinsically linked to the rhythm of the Nile. The very shape of the plateau, the precise placement of the pyramids within it, and the entire logistical system for moving colossal stone blocks was fundamentally dictated by the annual flooding of the river. To understand how the ancient Egyptians built these magnificent structures, we need to step back and truly appreciate the power and the predictability of the Nile's watery embrace. For nearly 6 months each year, as winter drew to a close, the Nile would swell dramatically. This wasn't a sudden violent outburst, but a slow, deliberate rise, a process fueled by the melting snow from the Ethiopian highlands and the Tibetan plateau. As the water level climbed, it would spread across the lower reaches of the Giza Plateau, transforming vast areas of arid desert into shimmering, muddy lakes. This wasn't a destructive force, though it was the key to everything. The Egyptians understood that the flood was not a random event, but a carefully observed and revered cycle, a gift that repeatedly provided them with fertile soil for agriculture, and, crucially, a navigable waterway. The Egyptians weren't simply building monuments, they were building with the river. The mud left behind by the flood, rich in silt deposited by the annual Nile inundation, was remarkably fertile. This wasn't merely a consequence of the flood. The Egyptians actively managed this floodwater. They constructed intricate systems of canals and dikes, a monumental undertaking in itself, to control the flow of the water. These weren't haphazard ditches. They were precisely engineered channels, carefully designed to direct the floodwaters across the plateau, creating temporary construction basins. These basins, often reaching several meters deep, were absolutely critical to the pyramid building process. The sheer scale of the stones, some weighing upwards of 80 tons, meant that transporting them overland was simply impractical over the rough, sandy terrain. The distances were too great, and the ground too unstable to allow for the use of wheeled carts. The Nile, however, offered a readily available, relatively level, and incredibly deep transport route. The Egyptians utilized a remarkable system of boats, essentially barges, to move massive blocks of stone from the quarries to the pyramid construction sites. These weren't sleek, modern vessels. They were flat-bottomed boats, often constructed of reeds and papyrus, designed to navigate the shallow, muddy waters. The boats were towed, most likely with teams of men pulling ropes, but it's increasingly believed that ramps and levers played a significant role. The Egyptians were brilliant engineers, and we have evidence that they experimented with various methods. Some researchers suggest that they employed a system of floating the stones, using a combination of rafts and levers to maneuver the blocks closer to the construction site. This wouldn't have been a single, continuous movement. Rather, the stones would have been repeatedly floated, guided by ramps, and carefully positioned. The water level itself was a tool. As the Nile rose, it provided a natural lift, making it easier to maneuver the heavy blocks. The Egyptians would likely have used a system of rollers and cradles, positioned within the water, to reduce friction and facilitate movement. The mud, saturated with water, acted as a natural lubricant, minimizing resistance. This process wasn't instantaneous. It was a slow, methodical, and incredibly demanding operation. Furthermore, the fluctuating water levels were used to shape the construction platforms. The Egyptians were adept at utilizing the shifting terrain. As the water receded, they would build up temporary ramps and platforms directly into the mud, effectively creating a series of stepping stones for the colossal blocks. The careful grading of the mud, controlled by the ebb and flow of the Nile, was fundamental to the construction process. The strategic placement of the pyramids within the Giza Plateau isn't accidental. The orientation of the Great Pyramid, for example, is remarkably aligned with cardinal directions, likely influenced by observations of the sun and stars, but also, subtly, by the patterns of the floodwaters. The Egyptians were acutely aware of the river's cyclical movements and how they affected the landscape. The Egyptians didn't just rely on the river's movement. They anticipated it. They built temporary docks and storage facilities along the riverbanks to prepare for the incoming floodwaters. They employed a vast workforce to construct and maintain these facilities, further demonstrating the scale of the project. The logistical network surrounding the Nile was a complex and incredibly sophisticated system, a testament to the ancient Egyptians' ingenuity and organizational abilities. The Nile, therefore, was not merely a backdrop to the construction of the pyramids. It was the very foundation of the entire operation. The predictability and power of the river's annual flood dictated the shape of the plateau, the flow of materials, and ultimately, the success of one of the greatest architectural achievements in human history. Without the Nile, the pyramids of Giza would have remained a distant, unattainable dream. The Giza Plateau, a monumental expanse of limestone and sandstone, wasn't always dominated by the colossal pyramids we know so well. Before the Great Pyramid of Khufu, before the smooth, sloping sides of Khafre's pyramid, there existed a simpler, yet equally important, form of royal tomb, the mastaba. These rectangular, flat-topped structures, constructed primarily of mud brick faced with smooth limestone, represent the crucial first step in the evolution of monumental Egyptian architecture, and they hold a key to understanding the foundations upon which the pyramids were built. Mastabas weren't built overnight. Their origins can be traced back to the pre-dynastic period, long before the rise of the pharaohs as we understand them. During this time, the people of Egypt, primarily farmers and craftspeople, built simple rectangular tombs for their deceased family members. These early tombs, often located within settlements, were constructed from readily available materials: mud brick, packed and hardened by the sun, and locally sourced stone for facing. The purpose was straightforward: to provide a secure resting place for the individual and to symbolically ensure their successful passage into the afterlife, a belief deeply rooted in the culture. As the early dynastic period, around 3100 BC, dawned, the practice of building tombs for the elite began to change. With the consolidation of power and the rise of the pharaohs as divine rulers, the tombs themselves began to reflect this increased status. The earliest pharaohs, such as Imhotep, the architect credited with designing the step pyramid of Djoser, recognized the need for more elaborate structures to honor their positions. Imhotep's ingenious solution was to stack mastabas one upon the other, creating the step pyramid, a revolutionary design that marked a significant departure from the traditional rectangular tomb. The step pyramid wasn't merely a collection of mastabas. It was a deliberate attempt to mimic the primeval mound from which the Egyptians believed the world had emerged, a symbolic connection to creation itself. The mastabas surrounding the step pyramid served a multi-faceted purpose. They housed the remains of the pharaoh's family members, including wives, children, and attendants. They were filled with grave goods, objects intended to accompany the deceased into the afterlife, such as food, pottery, furniture, weapons, and even servants, believed to provide for the needs of the individual in the next world. These goods weren't just luxuries. They represented the resources and power the deceased had possessed in life and were considered vital for a comfortable existence in the afterlife. The size and complexity of the grave goods varied depending on the pharaoh's wealth and status, demonstrating a clear correlation between earthly possessions and the ambition of eternal life. Following Djoser's reign, the mastaba form continued to evolve. The step pyramid itself was gradually covered with smooth limestone casing, further refining its appearance. Later pharaohs, such as Sekhemre Kutawi Sobek, constructed larger and more imposing mastabas, sometimes incorporating chambers and corridors within their structure. These later mastabas weren't simply extensions of the original step pyramid. They were often built independently, demonstrating a growing sophistication in architectural design. The walls of these later mastabas were frequently decorated with scenes from the deceased's life, religious beliefs, and depictions of the afterlife, providing a visual guide for the deceased's journey. A crucial development was the increasing use of ashlar blocks, precisely cut and dressed stone blocks within the construction of mastabas, particularly in the later periods. While mud brick and rough, hewn limestone remained common, the incorporation of ashlar blocks provided greater structural stability and allowed for more intricate designs. The quality of the stone used, fine Tura limestone, for instance, served as another marker of status and wealth, reinforcing the connection between material possessions and the deceased standing in the world. Furthermore, the layout of mastabas began to incorporate a sunken courtyard, a rectangular courtyard located beneath the level of the tomb floor. This courtyard, often surrounded by columns and walls, served as a sacred space for rituals and ceremonies, demonstrating a growing emphasis on religious practice within the tomb complex. The presence of these courtyards reflected a shift in understanding of the afterlife, moving beyond simple burial to encompass a more active, ritualistic engagement with the spiritual realm. By the time the Old Kingdom reached its zenith, the mastaba had become an integral part of royal tomb complexes, often appearing alongside the pyramid structures. The mastabas didn't replace the pyramids, rather, they complemented them, providing a sophisticated framework for the pharaoh's eternal residence and serving as a space for religious activities. The evolution of the mastaba, from its humble beginnings as a simple burial place to its complex integration within the pyramid complex, provides a fascinating insight into the development of Egyptian religious beliefs, architectural innovation, and the enduring desire to ensure a prosperous afterlife for the pharaohs and, by extension, for all Egyptians. The foundations of the pyramids were, in essence, built upon the careful planning and architectural expertise embodied within the silent, rectangular forms of the early mastabas. The construction of the Great Pyramids wasn't simply a matter of brute strength and manpower, as often depicted. While the sheer number of workers is astounding, estimates vary, but suggest tens of thousands to perhaps 100,000. A deeper look reveals a surprisingly sophisticated technological foundation. A key, and often underestimated, element of this foundation lay in the use of copper tools. These weren't the crude, imprecise instruments we might associate with early metalworking. The copper tools employed by the ancient Egyptians during pyramid construction exhibit a level of craftsmanship that reflects a surprisingly advanced understanding of metallurgy and material science. The discovery of copper tools within the pyramid complexes themselves, alongside traces of their use on the stone blocks, offers crucial evidence supporting this assessment. These tools weren't uniformly large or formidable. Instead, they appeared in a variety of sizes and shapes, suggesting a carefully considered range of applications. Analysis of these tools, primarily chisels, saws, drills, and punches, reveals that the copper used wasn't simply mined and hammered into shape. It was subjected to a complex process of heating, hammering, and shaping. The source of the copper itself is a fascinating puzzle. While the Egyptians had access to copper deposits in the Sinai Peninsula, the concentration and quality of the metal found within the pyramid sites suggest a more localized supply. Recent research points to the exploitation of copper deposits around the Fayum region, a fertile area north of Giza, as a primary source. The transport of this copper, likely by boat along the Nile, would have been a significant logistical undertaking in itself. The manufacturing process begins with copper ore, typically chalcopyrite, which contains varying amounts of copper and sulfur. The Egyptians didn't possess the technology to extract pure copper through smelting in the way we understand it today. Instead, they employed a technique called powdering, where the ore was repeatedly heated and hammered until it broke down into a fine powder. This process, though seemingly simple, was incredibly labor-intensive and created a significant amount of waste. The waste products, consisting of copper slag, were carefully collected and often used as a pigment in paints and other applications, demonstrating a circular economy approach. From this powder, the copper was reformed into shapes. Chisels, for instance, were produced by compacting the copper powder into molds, heating the molds to fuse the copper, and then hammering the resulting blanks into the desired shape. The precision achieved is remarkable, considering the limitations of the tools and the techniques. The angles and edges of these chisels were carefully controlled, allowing for precise cuts in the limestone blocks. Saws, too, were a product of this powdered copper process. These weren't the continuous blades we use today. Instead, they consisted of a copper rasp, a flat blade with teeth created by repeatedly hammering small pieces of copper onto a backing material, typically wood or bone. The copper rasp was then used to slowly abrade the limestone surface, creating a long, shallow groove. This method, though slower than modern sawing, produced remarkably accurate cuts, especially when combined with the careful application of pressure. Drills, essential for creating holes for dowels and joinery, represent another sophisticated application of copper tools. These drills, often referred to as twist drills, utilized a rotating motion to bore into the stone. The copper drill bit was heated and hammered repeatedly, generating friction and gradually cutting through the limestone. The Egyptians developed a technique of reaming, repeatedly drilling a small hole and then enlarging it with a larger drill to achieve a precise hole size. Punches, small copper hammers, used for creating holes by repeated impacts, were utilized extensively for shaping and forming the blocks, particularly for creating the slots where dowels would be inserted for joining blocks together. The hammering action, combined with the copper's malleability, allowed for intricate shaping and detailing. The use of copper tools didn't solely focus on cutting stone. It extended to the manipulation of wooden components used in the construction process, for example, shaping wooden wedges used to split stone blocks. The copper tools ensured a clean, precise finish, minimizing damage to the stone and reducing the effort required from the workers. The discovery of copper slag deposits around the pyramid sites further strengthens the evidence for their widespread use. These slag deposits contain traces of copper, as well as other metals and minerals, which confirms that the Egyptians were actively refining and working with copper during the pyramid construction. The careful selection of copper for toolmaking, its preparation, and the subsequent application demonstrate a sophisticated level of metallurgical understanding and engineering expertise. It's a subtle but vital component of the narrative of how the pyramids were built, showcasing the ancient Egyptians' skill, ingenuity, and technological prowess. The sheer scale of the Great Pyramid at Giza remains a monument to human ingenuity, but its construction hinges on a deceptively simple, yet incredibly complex question. How did the ancient Egyptians move those colossal stones? We know the stones, predominantly limestone from nearby quarries and granite from Aswan, weighed upwards of 80 tons, some approaching 100, a staggering burden for any civilization to handle. While the precise methods remain debated, archaeological evidence and careful experimentation have yielded several compelling theories centered around ramps, levers, and rollers, each playing a crucial role in the logistical ballet. Early theories often relied on a single, massive ramp constructed directly up the side of the pyramid. The idea is straightforward: build a long, gradual slope and simply push the blocks up it. However, the sheer length required for a ramp to reach the top of a structure as tall as the Great Pyramid presents immediate challenges. A ramp long enough to accommodate the necessary incline would have consumed an enormous amount of material, potentially rivaling the volume of the stones themselves. Furthermore, maintaining a consistent slope, especially as the pyramid grew taller, would have been extraordinarily difficult. The ramp would have become increasingly unstable, prone to collapsing under the weight of the stones and the workers attempting to move them. The angles required would have necessitated an almost impossibly long, wide structure, demanding an unsustainable amount of labor and resources. As this single ramp theory began to face scrutiny, researchers began exploring alternative approaches, with ramps frequently combined with the use of levers. Evidence suggests that numerous smaller ramps were likely employed, strategically placed around the pyramid's sides. These wouldn't have been continuous slopes, but rather stepped constructions, often constructed from mud brick faced with stone. The key here was the leverage offered by these ramps. Workers would have positioned themselves at the base of the ramp, using wooden levers to incrementally lift the stones as they were pushed upwards. The application of force, focused through a lever, dramatically increased the force exerted on the stone, allowing relatively few individuals to move a massive block. The geometry of levers, force multiplied by distance, provides a simple yet potent explanation for how such movement was achieved. Models and reconstructions have demonstrated the effectiveness of this system. A relatively small force, applied at the right point, can translate into a significant, upward lift. The concept of rollers also gained significant traction as researchers explored the possibilities. The presence of numerous, relatively small, rounded stones found within the pyramid complex strongly suggests their utilization. These stones, often smooth and polished, were likely employed to reduce friction beneath the massive blocks during movement. The theory proposes that workers would have positioned these rollers beneath a stone, effectively creating a low, friction surface. As the stone was pushed, the rollers would allow it to slide more easily, significantly lessening the force required to move it. The physics here is fundamentally linked to mechanics. Reducing friction is a cornerstone of efficient movement. Scientists have conducted experiments replicating this system, successfully demonstrating how the use of rollers can dramatically reduce the force needed to shift heavy objects. It's important to note that the system likely wasn't entirely static. The Egyptians wouldn't have relied solely on one method throughout the construction process. The initial stages, perhaps, involved the construction of a large, gentle ramp combined with lever systems. As the pyramid rose, the focus might have shifted towards utilizing rollers and smaller, more precisely angled ramps to navigate the increasing angles. Furthermore, the ground itself played a crucial role. The Egyptians carefully prepared the ground around the pyramid, compacting the soil to create a stable base for the ramps and rollers. This careful preparation reduced the risk of instability and ensured a smoother movement of the stones. The recovered evidence, including the distribution of stones, the layout of the construction site, and the types of tools found, indicates a highly organized and sophisticated approach. It wasn't a chaotic scramble, it was a meticulously planned operation. The scale of the operation suggests a large, skilled workforce, expertly coordinated to manage the logistics of moving these monumental blocks. The use of water, drawn from the Nile, is also suspected to have played a role, perhaps utilized to lubricate surfaces and facilitate the movement of rollers. Furthermore, recent research has focused on the potential use of sledges. Large, flat wooden platforms, dragged across the prepared ground, could have served as an extension of the lever system, facilitating the movement of stones over longer distances. The combination of ramps, levers, rollers, sledges, and a carefully prepared ground surface represents a remarkable feat of engineering, a testament to the ancient Egyptians' understanding of physics and their ability to translate that knowledge into a tangible, monumental achievement. It wasn't about brute force, it was about clever application of principles, coordinated effort, and a deep understanding of the materials at their disposal. The logistics of moving those stones remain a powerful reminder that even the most audacious endeavors can be accomplished through careful planning and ingenious solutions. The Great Pyramid of Giza isn't just a colossal tomb, it's a remarkably sophisticated instrument, a silent testament to the ancient Egyptians' profound understanding of the cosmos. For centuries, scholars and researchers have wrestled with the alignment of this monumental structure, searching for a deeper meaning beyond simply housing the remains of Pharaoh Khufu. Precise measurements taken over centuries reveal a level of accuracy that continues to astonish, suggesting a deliberate connection to the movements of the sun, moon, and stars. Early observations by Greek historians, notably Herodotus, documented the pyramid's orientation, noting that its sides were almost perfectly aligned with the cardinal directions north, south, east, and west. However, it wasn't until the 19th century, with the advent of modern surveying techniques, that the true scale of this alignment became apparent. Utilizing the plummet, level, and accurate distance measurements, British archaeologists, including William Strickland and John Maurice Howard, systematically charted the pyramid's orientation. They found that the north face was astonishingly accurate, deviating only by approximately 3 minutes of arcsy, a fraction of a degree. This is an extraordinary achievement, considering the limitations of the tools and knowledge available at the time. To put this into perspective, the error in measuring the Earth's circumference in antiquity was significantly larger. The key to understanding the alignment lies in the pyramid's orientation to the winter solstice sunrise. This is the most frequently cited and meticulously studied aspect of the alignment. When the sun rises on the winter solstice, December 21st, its first rays illuminate a dark niche cut into the eastern face of the pyramid. This, Benjamin's boat niche, as it's often called, is a precisely shaped cavity measuring approximately 4.7 meters long, 0.9 meters wide, and 2.6 meters deep. Its dimensions are not random. They are directly related to the angle of the rising sun at the winter solstice. Calculating the exact angle requires advanced trigonometry. The angle of the rising sun at the winter solstice is roughly 66 degrees and 24 minutes, which corresponds almost exactly to the angle of the Benjamin's boat niche. It's important to note that this alignment isn't simply a casual observation. It's a deliberate construction. The niche was meticulously carved and smoothed, demonstrating a high level of craftsmanship and a deep understanding of the principles of geometry. Beyond the winter solstice, research has revealed alignments with other celestial events. The pyramid's layout, particularly the shafts running through its core, has been linked to the rising and setting of the sun and moon throughout the year. These shafts, originally sealed, were later discovered to be oriented towards specific points in the sky. Measurements taken of the angles formed by these shafts, combined with the dimensions of the pyramid itself, demonstrate a remarkable awareness of the solar and lunar cycles. The most significant discovery regarding this alignment came in the 1990s with the work of Jean-Pierre Houdin and Mark Lehner. Utilizing computer modeling and detailed analysis of the shaft angles, they proposed a compelling theory. The shafts were designed to act as measuring instruments for the stars. Specifically, they identified that the shafts were aligned with the rising points of Sirius, the Dog Star, Orion's Belt, and the star Regulus during specific times of the year. The alignment with Sirius is particularly significant. The ancient Egyptians deeply revered Sirius, believing it to have a profound influence on the annual flooding of the Nile River, a vital event for their agriculture. The alignment with Sirius's rising point on the winter solstice coincided with the start of the inundation season, a period when the Nile flooded and its waters fertilized the land. This suggests a sophisticated system of calendar reckoning and a deep connection between the movements of the stars and the rhythms of life in ancient Egypt. Furthermore, the shafts weren't merely decorative. They served a practical purpose. As water slowly seeped through the shafts, the moisture created a cooling effect within the pyramid, helping to preserve the remains of Khufu and the treasures entombed within. This integrated approach, combining astronomical observation with practical engineering, demonstrates the ingenuity of the ancient Egyptian builders. The degree of precision attained in the Great Pyramid's alignment isn't just about aligning it with the stars. It reflects a complex system of mathematical and astronomical knowledge, likely developed over generations. It suggests that the pyramid wasn't just a tomb. It was a temple, a calendar, and a sophisticated instrument for understanding the universe. The ongoing research continues to reveal new layers of understanding, reinforcing the enduring mystery and magnificence of this iconic structure, a testament to the ambition, skill, and intellectual prowess of a civilization that gazed up at the stars and sought to incorporate their movements into the very fabric of their world. The Great Pyramid of Giza, a structure so monumental it continues to inspire awe and wonder millennia after its creation, holds secrets far more complex than simply stacked stone. While the ingenious methods of stone transport and the precise astronomical alignments are subjects of ongoing debate and meticulous study, a less obvious, yet equally fascinating, aspect of the pyramid's design involves a remarkably sophisticated system of internal ventilation. The conventional understanding of the pyramid as a tomb gradually shifted as researchers began to recognize the deliberate presence of shafts, narrow, slightly sloping passageways that extend throughout its core, and the surprising implications for airflow within the structure. These weren't merely decorative elements. They were integral to a system designed to regulate temperature and, potentially, to influence the perceived atmosphere within the pyramid's interior. The shafts themselves, numbering around 107, are consistently spaced, arranged in a geometric pattern that suggests a deliberate, not haphazard, design. Each shaft is typically around 15 centimeters in diameter, and they extend for varying distances, some ending abruptly within the core, others continuing deep into the pyramid's construction. Crucially, they aren't perfectly vertical. They exhibit a gentle, almost imperceptible, slope averaging approximately 1 centimeter per meter. This sloping design is the cornerstone of the airflow theory. The shape of the shafts, combined with the subtle slope, creates a natural funnel effect, allowing for a continuous, albeit slow, movement of air. Initial studies, utilizing sophisticated computational fluid dynamics, have allowed researchers to model airflow patterns within the pyramid's interior. These models demonstrate that air entering the Great Pyramid through the lower chambers, perhaps intentionally, would be channeled upwards by the sloping shafts. The theory posits that the primary entry point was located within the king's chamber, with air circulating through the shafts and eventually exiting through openings in the queen's chamber, potentially even at the very apex of the structure. The precise mechanics of this airflow are intricate. As air enters the king's chamber, the sloping shafts create a pressure differential. The air, being warmer and more humid from the lower, warmer levels of the pyramid, is drawn upwards due to this pressure difference. The subtle slope is essential. It's not just about a vertical shaft, but about a pathway that encourages the air to move consistently. Without the slope, the airflow would be significantly reduced and far less efficient. The size of the shafts, though small, was strategically chosen. A larger aperture would have created a more turbulent airflow, less desirable for a controlled system. The 15-centimeter diameter offered a balance sufficient to carry air, but also minimizing turbulence and maximizing the efficiency of the upward flow. Moreover, the shaft's construction, predominantly limestone, similar to the surrounding blocks, further contributed to the system's functionality. Limestone is relatively porous, allowing for a degree of air permeability that enhances the airflow. But the purpose of this ventilation system goes beyond simple temperature regulation. Ancient Egyptians placed immense importance on the perceived atmosphere of sacred spaces. The air we breathe isn't simply a mixture of gases. It carries subtle variations in humidity, temperature, and even the presence of trace elements. By facilitating a consistent flow of air, the pyramid's shafts likely created a more stable and pleasant atmosphere, reducing the oppressive heat and humidity that could build up within the massive stone structure. Furthermore, the slow, continuous movement of air could have subtly altered the perception of sound. The reverberation of voices within the pyramid's chambers might have been subtly influenced by this airflow, creating an ethereal quality, perhaps intentionally designed to enhance the experience of solemn contemplation or ritual. The discovery of traces of moisture within the shafts has also provided valuable insights. While the exact source of this moisture remains a subject of research, it's believed to be a combination of condensation, water vapor collecting on the cooler surfaces of the shafts, and perhaps even minor seepage from the surrounding bedrock. This moisture, in turn, likely influenced the airflow, potentially dampening the air slightly and further regulating the temperature. It's important to acknowledge that the ventilation system's full purpose is still debated. Some researchers believe it was purely functional, designed to maintain a comfortable internal environment. Others propose a more symbolic interpretation, suggesting that the shafts were connected to the ancient Egyptians' beliefs about the afterlife. They might have been seen as channels for the spirit's ascent, or as conduits for the breath of life itself. Regardless of the precise intention, the discovery of the Great Pyramid's ventilation shafts represents a remarkable achievement in ancient engineering and a testament to the Egyptians' understanding of airflow dynamics. It underscores the fact that the Great Pyramid was not simply a tomb, but a complex, carefully designed structure, incorporating multiple sophisticated systems, including this remarkable ventilation network, to create a space that was not only structurally sound, but also, perhaps, spiritually resonant. It reminds us that even the most monumental structures are built upon a deep understanding of the natural world. The very stones of the pyramids, those enormous blocks of limestone and granite, aren't simply rock. They're a complex chemical recipe, a geological cocktail that has, remarkably, allowed them to endure for thousands of years. Scientists have painstakingly unraveled the secrets hidden within these materials, revealing a fascinating story of formation, alteration, and, crucially, the chemical processes that underpin their astonishing longevity. The initial limestone, quarried from the Tura and Aswan regions, is overwhelmingly composed of calcium carbonate. That's limestone's primary ingredient. However, it's not a uniform, pure form. The exact proportions vary slightly depending on the source, but typically it's around 73–82% calcium carbonate, with the remaining percentage consisting of a surprising mix of other minerals. Among the most abundant of these secondary components is calcite, a crystalline form of calcium carbonate. The precise ratio of calcite to pure calcium carbonate can fluctuate, often influenced by the conditions present during the stone's formation. In Tura, for example, the limestone often contains a higher percentage of calcite, while the Aswan limestone tends to be richer in dolomite, a mineral composed of calcium-magnesium carbonate. Understanding this compositional variation is important, as it can subtly affect how the stone responds to environmental stresses later in its existence. These differences aren't random. They're tied to the ancient sea conditions and geological processes that shaped the region. Beyond the major components, trace amounts of other minerals are detectable. Quartz, often present in the form of microcrystalline fragments, contributes to the stone's hardness and resistance to weathering. Feldspars, a group of silicate minerals, are also common, though their concentration is typically lower. Clay minerals, though not always readily apparent, are frequently found within the limestone matrix, and their presence can have a significant impact on the stone's permeability, how easily water and gases can pass through it. The level of clay content, particularly, is a critical factor in determining the stone's vulnerability to dissolution. The chemical processes that have operated on the pyramid limestone since its construction have been remarkably gentle, largely due to the stone's inherent properties. The low permeability of the stone, particularly when relatively dry, has played a vital role. Water, the primary agent of chemical weathering, can't easily penetrate and react with the material. This resistance to water ingress has dramatically slowed down the natural processes that would otherwise break down rock formations. However, the stone isn't entirely immune. The most significant chemical reaction impacting the pyramids is a slow, almost imperceptible process called carbonation. Rainwater, even when slightly acidic, contains dissolved carbon dioxide, a byproduct of respiration, and the breakdown of organic matter. When this rainwater comes into contact with the calcium carbonate in the limestone, a chemical reaction occurs. Carbon dioxide reacts with the calcium carbonate, forming calcium bicarbonate, a soluble compound. This process slowly dissolves the limestone, creating tiny cavities. The rate of this carbonation is incredibly slow. It's estimated that under ideal conditions, a few millimeters of limestone might dissolve over thousands of years. The fact that this dissolution is so gradual is key to understanding the pyramid's preservation. The construction techniques employed, particularly the meticulous placement of the stones, creating a dense, interlocking structure, further minimized the impact of water. The joints between the blocks, while present, are designed to shed water efficiently rather than creating channels for prolonged exposure to the elements. Furthermore, the stone's chemical composition itself, particularly the presence of silica and the relatively low clay content, contributes to a degree of inherent resistance to chemical attack. Scientists have conducted detailed analyses of pyramid limestone samples using techniques like X-ray diffraction and Raman spectroscopy. These methods allow them to identify the precise mineral composition, map the distribution of different components, and even detect microscopic changes that have occurred over time. These analyses have revealed fascinating information about the stone's past. For instance, evidence of alteration due to ancient flooding events or the slow creep of calcite crystals within the stone structure. Interestingly, the deeper within the pyramid structures, the stone often shows a slightly different chemical signature. This suggests that the outer layers, exposed to the full force of the Egyptian climate, have undergone more significant alteration than the inner chambers, where conditions were somewhat more stable. The outer surfaces, frequently impacted by wind-blown sand and fluctuating temperatures, have experienced greater levels of physical and chemical weathering. The ongoing study of pyramid limestone isn't simply about understanding the past, it's also about informing conservation efforts. By continuing to monitor the stone's chemical state and understand the factors that influence its stability, scientists can develop strategies to mitigate any potential damage from modern environmental stresses. The pyramids aren't just monuments, they are living geological records, and their continued survival is a testament to the power of chemical equilibrium and the remarkable tenacity of ancient materials. The careful balance of elements within these stones, combined with human ingenuity in their construction, has created a legacy that resonates through millennia. The ancient Egyptians didn't simply stack massive blocks of stone. A truly remarkable feat of engineering, and perhaps even magic to those who first witnessed it, was the way they held these colossal pieces together. The key to this incredible stability lay not just in the precisely cut and fitted blocks themselves, but in the ingenious and remarkably consistent mortar that bound them. This wasn't a single, standardized substance. Rather, a fascinating range of recipes and bonding agents were utilized, reflecting a deep understanding of material properties and the environment. Archaeological investigations, particularly around the step pyramid of Djoser at Saqqara, have yielded incredibly detailed clues about this practice. The remains of mortar samples, analyzed through modern techniques like X-ray fluorescence and microscopy, reveal a composition far more complex than a simple mixture of lime and sand. Initially, the prevalent assumption was that a straightforward concoction of powdered limestone, calcined stone, and water provided the necessary grip. However, further study demonstrated a significant variation in the proportions and, critically, the addition of other materials, suggesting a tailored approach based on the specific stone being used and the conditions of its preparation. One commonly found component was natron, a naturally occurring salt mixture consisting primarily of sodium carbonate, sodium bicarbonate, and sodium chloride. Natron played a dual role. First, it acted as a powerful desiccant, intensely drawing out moisture from the limestone before the mortar was mixed. This was absolutely vital, as water would severely weaken the bond. Second, the sodium salts in natron reacted with the calcium in the limestone, forming calcium-sodium silicates complex compounds that dramatically enhanced the mortar's adhesive properties. These silicates created a strong, interlocking network within the stone, leading to a far superior bond than simply relying on water alone. The recipe for mortar around Djoser's step pyramid included a surprisingly high percentage of natron, sometimes as much as 40% by volume. This demonstrates a meticulous focus on minimizing water content, a fundamental principle in creating durable stone adhesives. Excavations have uncovered large drying yards, essentially open, air workshops, where blocks of limestone were deliberately exposed to the sun and wind, significantly accelerating the drying process and maximizing the effectiveness of the natron treatment. Beyond natron, evidence suggests the inclusion of gypsum, a calcium sulfate mineral, was frequently incorporated, particularly in areas requiring exceptional strength and resistance to weathering. Gypsum possessed a remarkable ability to react with water, creating a paste-like consistency and further cementing the stone together. It also contributed to the mortar's plasticity, making it easier to work with when shaping and applying it to the blocks. The methods of mixing were likely quite simple, reflecting the practical nature of ancient Egyptian construction. Large vats, constructed from mud brick or stone, would have been filled with the calcined limestone, natron, gypsum if used, and a carefully measured quantity of water. Workers would have used wooden tools, paddles, and shovels to thoroughly mix the ingredients, paying particular attention to ensure a homogeneous consistency throughout the mixture. The water was typically added slowly, allowing the chemical reactions to proceed gradually and preventing the formation of lumps. Interestingly, the color of the mortar varied depending on the specific recipe and the presence of different minerals. Some samples exhibited a reddish hue, attributed to the presence of iron oxides, common impurities in limestone, while others were a pale gray or white, reflecting the purity of the materials. This variation likely wasn't a mistake. It may have served as a visual indicator of the mortar's quality and consistency. The application of the mortar was a carefully controlled process. Blocks were typically placed onto temporary wooden supports, and the mortar was then applied with trowels or hand-held tools. The workers would meticulously fill the joints between the blocks, ensuring a tight, uniform layer. Once applied, the mortar would be allowed to cure slowly, gradually hardening through a process of hydration, a chemical reaction with water, which is what gives concrete its strength. The longevity of the pyramids, standing for thousands of years, despite the harsh Egyptian climate, speaks volumes about the effectiveness of this mortar. It's clear that the ancient Egyptians possessed an extraordinarily sophisticated understanding of material science, creating a binding agent that not only held these immense stones together, but also contributed significantly to the enduring stability of these incredible monuments. Their expertise in combining natural materials, understanding their reactivity, and carefully controlling the curing process represents a remarkable achievement in engineering and a testament to the ingenuity of a civilization long past. The sheer scale of the pyramids, those monumental structures rising from the sands of Egypt, immediately begs the question, who built them? It's a captivating thought, often simplified to images of countless, weary slaves toiling under the relentless sun. While forced labor undoubtedly played a role, a far more nuanced and complex reality emerges when we examine the archaeological evidence. The construction of the pyramids was In fact, a remarkably organized undertaking, relying on a workforce comprised of a diverse range of skilled laborers, support staff, and a discernible social hierarchy. A carefully constructed system designed to maximize efficiency and maintain order. Early theories, fueled by ancient Greek writers, painted a grim picture of thousands of enslaved people, whipped and driven to exhaustion. However, recent discoveries have dramatically shifted this perspective. Examination of worker settlements surrounding the pyramid sites, particularly those found at Giza and Saqqara, reveals a far more organized and, surprisingly, comfortable existence for the people involved. These settlements, dubbed mastabas, or worker villages, were not places of brutal confinement, but rather communal living spaces. Excavations have unearthed evidence of bakeries, breweries, and even small-scale workshops, indicating a level of self-sufficiency and a degree of specialization among the workforce. Houses were generally modest, built with mud brick and featuring courtyards, suggesting a degree of privacy and a reasonable standard of living. The workforce wasn't a monolithic mass. It was segmented into different strata, reflecting the administrative and organizational structure of ancient Egyptian society. At the top were the overseers, architects, and master builders, the skilled workers, as they've been termed by archaeologists. These individuals possessed specialized knowledge of mathematics, astronomy, engineering, and stonemasonry. They were likely recruited from among the higher classes, perhaps even the nobility, and were responsible for planning the construction, ensuring the accuracy of the measurements, and supervising the various stages of work. The intricate chambers and passageways within the pyramids, such as the ventilation shafts explored in Part 7, were undoubtedly designed and overseen by these master builders. Beneath them were the skilled artisans, stonemasons, carpenters, metalworkers, and sculptors. These individuals were responsible for crafting the decorative elements, constructing the wooden frameworks, and shaping the massive limestone blocks. Evidence from the sites points to a considerable number of these artisans, suggesting a significant investment in specialized craftsmanship. They weren't simply raw laborers. They possessed a level of training and expertise, and their work contributed significantly to the aesthetic and structural integrity of the pyramids. The majority of the workforce, however, consisted of what are often described as menial laborers, farmers, seasonal workers, and perhaps even villagers brought in for specific periods during the building process. These individuals performed the heavy lifting, transporting the blocks, and undertaking the more physically demanding tasks. Evidence suggests that these workers were provided with rations including bread, beer, and meat, and that they were organized into teams with assigned duties and a system of rewards. The discovery of a mate-bone bed at Giza, along with the remains of butchered animals, provides compelling evidence of this logistical support. A crucial element in understanding the workforce was the system of labor organization. Archaeological evidence, including the discovery of tool caches and the arrangement of the worker settlements, indicates a sophisticated system of task assignment and rotation. Teams were likely assigned to specific tasks for extended periods, fostering a sense of responsibility and teamwork. This system, combined with the provision of food and accommodation, likely reduced the need for constant coercion and increased worker productivity. The social hierarchy wasn't simply a matter of skill level. It was deeply intertwined with the religious beliefs of the time. The pyramids were not merely tombs. They were considered gateways to the afterlife, and their construction was seen as a sacred duty. The workers, therefore, were actively involved in ensuring the pharaoh's successful journey to the next world. This religious significance, coupled with the organizational structure and logistical support, created a powerful incentive for participation and contributed to the overall efficiency of the project. Interestingly, the discovery of a large, central courtyard within many of the workers' settlements suggests a role for communal gatherings and religious ceremonies. This space would have been used for religious rituals, feasts, and celebrations, reinforcing the connection between the workers' labor and the pharaoh's divine authority. The sophisticated logistics involved in supplying the workforce is also remarkable. The discovery of wells and the organization of transportation routes, likely utilizing oxen-drawn carts, demonstrate a sophisticated understanding of water management and supply chains. The ability to consistently provide food, tools, and other necessities was paramount to the success of the construction project, and it's clear that the Egyptians possessed a remarkably organized system for managing these resources. The workforce of the pyramids, therefore, was not a story of brutal oppression, but one of carefully managed, organized labor. It was a testament to the advanced social, logistical, and engineering capabilities of ancient Egypt, a society that understood the importance of incentivizing its people, utilizing specialized skills, and aligning its efforts with its deeply held religious beliefs. The sheer scale of the pyramids remains a stunning achievement, and a critical part of that achievement rests on the complex, surprisingly comfortable, and profoundly organized lives of the people who built them. The immense structures of the ancient pyramids weren't simply feats of engineering. They were profound expressions of a worldview, a meticulously crafted attempt to grapple with the most fundamental human questions. What happens after we die? And how can we best ensure a successful transition to the next stage of existence? Archaeological discoveries and analyses of the pyramid interiors reveal a startlingly complex and consistent religious belief system, one that shaped every aspect of the construction process, from the orientation of the structures to the placement of artifacts within. The Egyptians, unlike many civilizations of the time, didn't simply bury their dead and hope for the best. Their understanding of death was intimately connected to the cyclical nature of the cosmos, a concept woven into the very fabric of their lives and reflected dramatically in their monumental tombs. Central to this belief was the concept of Ma'at, a core Egyptian principle representing truth, justice, harmony, and cosmic order. Maintaining Ma'at was paramount, not just in daily life, but also in the afterlife. The deceased needed to be reintegrated into this established order, a process facilitated by a meticulously prepared journey. The pyramid itself served as a crucial component of this journey, a physical embodiment of the steps required to achieve this reintegration. The ascending structure, with its series of chambers and passageways, mirrored the journey of the sun god Ra as he traveled across the sky each day, battling the forces of chaos and darkness to bring forth light and renewal. The Great Pyramid of Giza, for example, is often interpreted as a precise architectural representation of this solar journey. The King's Chamber, located deep within the pyramid's core, was considered the ultimate destination, representing Ra's arrival at his highest point of power. The narrow passageways leading to this chamber were deliberately designed to create a sense of constriction and difficulty, simulating the trials and tribulations faced by the deceased as they navigated the dangers of the underworld. This wasn't seen as a punishment, but rather as a test of their worthiness, a confirmation of their adherence to Ar-Amat. The chambers themselves were filled with an astonishing array of objects, carefully chosen to sustain the deceased in the afterlife. These weren't meant to be merely decorative. They were intended to provide the individual with everything they would need: food, drink, clothing, furniture, weapons, and even servants represented by Shabti figurines, small statues designed to perform labor for the deceased. The sheer volume of goods discovered within royal tombs, like that of Tutankhamun, points to the deeply held belief that the afterlife would be a continuation of earthly life, albeit one requiring significant resources. However, the placement of these objects held profound symbolic meaning. The orientation of the objects within the chambers wasn't random. Studies have suggested that the positioning of certain items, particularly those associated with royal power, such as scepters, false beards, and ceremonial garments, reinforced the deceased's status as a divine ruler in the next world. The placement of canopic jars, which contained the mummified organs of the deceased, was particularly significant. Each jar was dedicated to one of the four sons of Horus, deities who protected and oversaw the vital organs, ensuring their proper functioning in the afterlife. Beyond the materials and placement, the walls of the burial chambers were frequently adorned with intricate carvings and paintings. These scenes depicted the deceased making offerings to the gods, participating in religious rituals, and receiving guidance from the spirits of the dead. The famous Book of the Dead, a collection of spells and prayers intended to assist the deceased in navigating the perilous journey through the underworld, was often placed within the tombs. The spells weren't simply recited. They were believed to be actively invoked, influencing the course of events and ensuring the deceased's safe passage. The use of colors in these depictions is also noteworthy. The Egyptians employed a sophisticated understanding of pigment chemistry, utilizing minerals like azurite, malachite, and lapis lazuli to create vibrant hues. Blue, in particular, represented the heavens and the waters of the primordial chaos from which creation emerged. The careful application of these colors, and the symbolic meaning imbued within them, underscored the importance of aligning oneself with the divine order. The pyramid's orientation, specifically its alignment with cardinal directions, further reinforced this connection to the cosmos. Precise astronomical alignments, achieved through careful observation of the stars and sun, established a direct link between the earthly realm and the celestial sphere, strengthening the belief that the deceased could, in essence, return to the source of all creation. The pyramid wasn't just a tomb, it was a carefully constructed microcosm of the universe, designed to facilitate the deceased's successful integration into its eternal rhythms. The pyramid's solid, enduring construction represented a desire for permanence, a tangible manifestation of the hope for an eternal existence, guided by the principles of Urs Mot and sustained by a profound understanding of the cyclical nature of life, death, and rebirth. The heart of every pyramid, the space intended for the pharaoh's eternal rest, was the burial chamber. It wasn't a simple room, it was a complex, carefully constructed sanctuary designed to facilitate a seamless transition into the afterlife, a concept deeply woven into the fabric of ancient Egyptian belief. While the outer grandeur of the pyramid, the towering stone blocks, the sloping sides served a symbolic purpose. The chamber within was the locus of the most significant rituals and the focus of the most meticulous planning. Understanding its dimensions and the artistry applied within offers a profound insight into the Egyptians' understanding of death, preservation, and their hopes for eternity. The dimensions of these chambers varied considerably across the different pyramid complexes. The Great Pyramid of Giza, the largest of the ancient wonders, boasts a central burial chamber, known as the King's Chamber, which is a remarkable feat of engineering. Its dimensions are roughly 10.1 meters, 33 feet long, 5.3 meters, 17 feet wide, and 7.3 meters, 24 feet high. The walls are constructed of massive granite blocks, a material chosen for its exceptional durability and resistance to erosion. The ceiling is a relatively shallow, sloping surface designed to minimize the weight distribution and reduce the structural stress on the walls. Notably, the chamber is empty of any funerary equipment. It contained no sarcophagus, no treasures, and no decorations beyond the carefully laid granite blocks. This stark simplicity suggests a focus on the space itself as a vessel for the pharaoh's spirit, rather than a repository of earthly possessions. Moving to the step pyramid of Djoser at Saqqara, the earliest known example of a pyramid, reveals a significantly different approach. Here, the main burial chamber, located within the step pyramid itself, was considerably smaller, approximately 5.3 meters, 17 feet long, 2.8 meters, 1,009 feet wide, and 3.7 meters, 12 feet high. While still constructed of stone, the walls were decorated with intricate carvings, primarily featuring depictions of the pharaoh, Djoser, receiving offerings from his officials. These carvings were painted with vibrant colors, blues, greens, reds that have remarkably survived the passage of millennia. This early chamber was furnished with a stone sarcophagus, and alongside it, a collection of pottery vessels, food, and other items believed to be needed by the pharaoh in the afterlife. The design highlights a more pragmatic approach to burial, anticipating the pharaoh's material needs in his new existence. Beyond the primary chambers, many pyramids contained additional rooms and corridors, often referred to as annexes or side chambers. These spaces served a variety of purposes, including storage for funerary goods, spaces for priests to conduct rituals, and sometimes even rooms intended for temporary habitation by the priests during the elaborate burial ceremonies. The Valley Temple, connected to the pyramid, often housed these rooms, and access was controlled through a series of corridors and gateways. The specific layout and function of these ancillary spaces varied greatly, depending on the pyramid's age, the pharaoh's reign, and the prevailing religious beliefs. The decoration of the burial chambers wasn't merely aesthetic, it held profound symbolic significance. Hieroglyphic texts, carefully inscribed on the walls and ceilings, served as spells and prayers designed to guide the pharaoh's spirit on its journey through the underworld. These texts, primarily excerpts from the Book of the Dead, contained instructions for navigating the dangers of the afterlife, ensuring the pharaoh's safe passage to Osiris, the god of the underworld. The imagery itself, depictions of gods, goddesses, and mythological scenes, was intended to reinforce these prayers and assist the pharaoh in his transition. The colors used in the decorations were also considered vital. Red, for example, was associated with vitality and resurrection, while blue represented the heavens and the waters of the underworld. Rituals associated with the burial chamber were elaborate and meticulously timed. The opening of the mouth ceremony, perhaps the most significant, was performed immediately after the pharaoh's body was placed within the chamber. This involved priests inserting slivers of obsidian, quartz, and carnelian into the pharaoh's mouth, symbolizing the restoration of his ability to speak and consume in the afterlife. It was believed that without this ceremony, the pharaoh's spirit would be unable to communicate or receive sustenance. The chamber itself was sealed, often with a massive stone lid or false door, to protect the pharaoh's remains and ensure the sanctity of the space. The precise rituals conducted, including the duration of the sealing, are subjects of ongoing research and scholarly debate. The study of these burial chambers continues to reveal new insights into ancient Egyptian beliefs and practices. Technological advancements, such as ground-penetrating radar and 3D laser scanning, are allowing archaeologists to explore these spaces with unprecedented detail, uncovering hidden chambers, documenting the original layout, and analyzing the materials used in their construction. The care taken in their design and decoration speaks to the Egyptians' deep-seated belief that death wasn't an end, but a transition, a passage to a new and eternal realm, a realm they sought to prepare for with meticulous precision and profound spiritual significance. The desert wind whispered across the limestone face of the Great Pyramid of Giza, carrying with it the scent of sand and millennia, while the vast chambers and imposing structure itself spoke volumes about the power and ambition of Pharaoh Khufu. A quieter, more intimate narrative resided within the smaller, often overlooked spaces, a narrative etched in stone, revealed through the careful study of cartouches. These weren't mere decorative flourishes, they were keys, painstakingly crafted to unlock the names and titles of the pharaohs themselves, and crucially, to reveal their connection to the divine. The concept of a cartouche originated with the ancient Egyptians, developing from earlier systems of royal identification. Initially, royal names were simply enclosed in an oval frame, a simple and effective way to distinguish them from the names of commoners. However, as the Old Kingdom evolved, particularly during the Fourth Dynasty, the age of the Great Pyramids, this evolved into a highly formalized and symbolic form. The oval shape itself, a stylized representation of the seat of a pharaoh, the sad seat, immediately conveyed authority and status. It wasn't just a frame, it was a miniature throne, a visual representation of the ruler's power. The discovery of cartouches within pyramid complexes wasn't a singular event. They were found sporadically, often during the meticulous archaeological work undertaken by figures like James Westmacott in the 19th century. But it was the work of Giovanni Belzoni, an early explorer, in 1842, that brought widespread attention to their significance. He unearthed a collection of cartouches from within the north-east corridor of the Great Pyramid, revealing the name of Khufu himself, the Nechereket, the Lord Khufu. The significance of this find, coupled with similar discoveries in other pyramids, sparked a frenzy of investigation into the royal names and their association with the gods. The cartouches weren't consistently rendered. There were variations in the style of the oval frame itself. Some were more elaborate, with intricate detailing, while others were simpler. The hieroglyphs within the cartouche, the sacred carvings, were also subject to subtle differences. This variation wasn't random. It reflected the evolution of Egyptian writing, the differing skills of the scribes, and perhaps, intentionally, the desire to emphasize certain aspects of the pharaoh's name and title. The hieroglyphs themselves weren't just a phonetic representation of the name. Each symbol carried a specific meaning, a sacred association. For example, the glyph for Necher, Lord, signified the pharaoh's connection to the divine realm. Khut, Khufu, was the royal name, a personal identifier, but its inclusion within the cartouche amplified its importance, linking the pharaoh directly to the god's power. The careful placement of these symbols, the precise arrangement of the hieroglyphs within the oval, was dictated by complex religious and cosmological beliefs. One of the most fascinating aspects of studying these cartouches is the realization that many pharaohs were associated with multiple deities. The name As-Nechereket, for instance, wasn't just Khufu's royal name. It was also linked to the god Ra, the sun god, a connection vital to the Egyptians' understanding of the universe. The cartouche served as a visual reminder of this fundamental relationship, reinforcing the pharaoh's role as an intermediary between the earthly and divine realms. Similarly, the cartouche of Unas, for instance, demonstrated a close relationship with Horus, the falcon-headed god, illustrating the complex web of religious associations surrounding royal power. The discovery of cartouches within the Pyramid of Djoser, the architect of the step pyramid at Saqqara, proved particularly insightful. The cartouche of Djoser contained not only his name, Saqqamket, but also included symbols linked to Osiris, the god of the afterlife, further solidifying the pharaoh's role as the ruler of the underworld and guarantor of eternal life. This demonstrates a trend: the more elaborate the pyramid, the greater the emphasis on the pharaoh's connection to the gods and their corresponding domains. The study of these cartouches, isn't just about deciphering names. It's about understanding the deeply ingrained worldview of the ancient Egyptians. They believed that a pharaoh's life was inextricably linked to the fate of the cosmos. By associating themselves with powerful gods, the pharaohs sought to ensure their continued existence in the afterlife and ultimately to maintain the stability of the world. Each cartouche, painstakingly carved and meticulously placed, was a testament to this belief, a silent plea for immortality, and a powerful statement of royal authority. The continued analysis of these ancient inscriptions, combined with advances in radiocarbon dating and archaeological techniques, continues to refine our understanding of the complex religious and political landscape of the Old Kingdom, offering a glimpse into the minds of those who built these magnificent structures and, more importantly, their enduring faith. The sands of Egypt, shifting and whispering secrets for millennia, held a quiet mystery that wasn't revealed until the meticulous work of 19th-century archaeologists. For centuries, the Grand Pyramids of Giza and Saqqara, along with countless smaller structures across the land, had been seen as simply impressive tombs. The focus was on the king's final resting place, the immense burial chamber, the ornate sarcophagus, and the vast quantities of treasures buried alongside the deceased. However, as excavation techniques advanced, and with the guidance of the increasingly sophisticated understandings of ancient Egyptian belief, a new layer of understanding began to emerge: the careful construction and purpose of what became known as false doors. Early explorations, particularly those led by Giovanni Belzoni in the 1840s, primarily sought to recover the opulent contents of royal tombs. While he uncovered some remarkable artifacts, a chariot, a statue of King Amenemhat III, and even a substantial collection of canopic jars, Belzoni's investigations didn't fully grasp the significance of the smaller, more inconspicuous openings he encountered. These openings, often concealed behind painted scenes or intricately carved panels, were dismissed as structural quirks, perhaps simply the result of imperfections in the stone or unintended gaps during construction. The prevailing attitude was one of material recovery, and the preservation of the building's integrity took a distant second. The breakthrough came with the work of Auguste Mariette, a French archaeologist who established the Egyptian Museum in Cairo. Mariette, a staunch advocate for preserving and studying Egyptian antiquities, brought a different approach. He recognized that the walls of the pyramids were not simply meant to be adorned. They were imbued with a profound symbolic meaning. Mariette began to meticulously document the locations and characteristics of these false doors, noting their size, the materials used in their construction, often a painted limestone, carefully mimicking the appearance of a genuine doorway, and the scenes depicted on their surrounding walls. What began to reveal itself was a sophisticated system intricately linked to the Egyptian belief in the afterlife. The false doors weren't merely decorative. They were understood to be actual pathways, not for physical passage, but for the spiritual journey of the deceased. The Egyptians believed that death was not an end, but a transition to another realm, a mirrored version of the world they had left behind. This journey, known as the Kai journey, required specific provisions and rituals to ensure a successful transition and a comfortable existence in the afterlife. The scenes painted on the walls around the false doors were crucial to this process. Most commonly, these scenes depicted the deceased being greeted by various deities, offering them food, drink, and other necessities. For example, a false door might show Osiris, the god of the underworld and resurrection, presenting the deceased with loaves of bread and jugs of beer, staples of the Egyptian diet, and symbols of nourishment and abundance. Other scenes could feature Hathor, the goddess of motherhood and joy, offering the deceased a sistrum, a musical instrument believed to bring good fortune. These offerings weren't simply visual representations. Egyptians sincerely believed that the deities were actively responding to the presence of the deceased. Ka, the vital life force that needed sustenance to continue its journey. The placement of the false doors themselves was also significant. They were almost always located on the eastern face of the pyramid, the direction of sunrise, representing rebirth and the start of a new day. The eastern side was considered the most sacred, closely associated with the rising sun god Ra. The doors were typically positioned to receive the morning sunlight, which was thought to empower the deceased's Ka and facilitate its ascent to the heavens. Interestingly, the size of the false doors was carefully calibrated. They were generally quite small, often only a few feet tall, reflecting the scale of the Ska, which Egyptians considered to be a miniature version of the human being. The small size also served as a symbolic restriction. The Kai could only pass through the doorway with the permission of the gods. Beyond the depictions of deities and the access to sustenance, the false doors served another crucial function. They provided a conduit for communication between the deceased and the living. The Egyptians believed that the living could, and even should, maintain a relationship with the deceased, offering prayers and performing rituals to aid their journey. The small openings allowed for the passage of prayers and offerings, ensuring that the Ska remained connected to its family and could receive their support. Further study, particularly the work of Flinders Petrie and his team in the late 19th and early 20th centuries, revealed a remarkable level of standardization in the construction and decoration of false doors across different pyramids. This suggests that these structures were not haphazard additions, but rather were part of a carefully designed and consistently implemented religious system. The discovery of false doors provided a deeper, more nuanced understanding of the Egyptian conception of death, the afterlife, and the profound connection between the physical and spiritual realms. They demonstrated that the pyramids were more than just tombs. They were sophisticated temples, designed to facilitate the eternal journey of the pharaohs, a journey of nourishment, communication, and ultimately, eternal life. The desert wind, a constant whisper across the Giza Plateau, carried with it more than just sand. For decades, a subtle, persistent question had haunted researchers investigating the Great Pyramids, a question centered not on their colossal scale or their precise alignment, but on the unusual quiet that often seemed to envelop them. It wasn't simply a matter of the vastness of the surrounding landscape, though that undoubtedly played a role. Scientists began to suspect something more profound was at work, something linked to the very way the pyramids were built. A hidden acoustic property. Early investigations, conducted primarily in the late 20th and early 21st centuries, utilized highly sensitive microphones and sophisticated acoustic mapping technology. The initial goal was straightforward: to measure and understand the sound transmission characteristics within the pyramid chambers and corridors. What they discovered was astonishing. Sound, rather than traveling freely throughout the structures, seemed to be significantly dampened and redirected. It was as if the pyramids possessed an inherent ability to absorb and diminish sound waves. The construction itself offers the first clues. The blocks used to build the pyramids, primarily limestone quarried locally and granite brought from Aswan, were not simply stacked haphazardly. They were meticulously fitted together, a feat of engineering that involved incredibly tight joints. But these joints weren't just held together by mortar. They were shaped with astonishing precision, often featuring a complex interlocking design. This level of detail wasn't merely for structural stability. It actively disrupted the flow of sound. When sound waves entered the pyramid, they encountered these irregular surfaces, causing them to scatter and refract. Think of shining a light on a rough stone compared to a smooth one, the rough surface breaks up the light, creating a dappled effect. The pyramid blocks acted in a similar manner for sound. Furthermore, the materials themselves contributed significantly. Limestone, being porous and containing numerous small air pockets, naturally absorbed sound. The granite, denser and more solid, provided even greater sound dampening capabilities. But the Egyptians weren't relying solely on material properties. They also incorporated a honeycomb technique, where they deliberately left small voids within the blocks themselves. These cavities, far from being imperfections, were carefully designed to resonate in specific ways, further contributing to the scattering of sound waves. The resulting effect was akin to a complex acoustic labyrinth, a carefully crafted system to contain and control sound. The investigation extended beyond simple measurements. Scientists employed techniques like acoustic tomography, essentially creating a three-dimensional map of sound propagation within the pyramid. This revealed complex interference patterns, with certain areas exhibiting drastically reduced sound levels compared to others. The data suggested that the pyramids weren't simply absorbing all sound. They were actively channeling it, directing sound waves around obstacles and concentrating them in specific zones. One particularly intriguing aspect of the research focused on the lower chambers, often less explored due to their tight confines and the challenges of conducting measurements. Here, the sound dampening effect was most pronounced. Researchers theorized that this was partly due to the increased density of the blocks and the presence of sealed air pockets, creating a highly resonant environment. The controlled dampening of sound within these areas raised questions about their intended purpose. Were they specifically designed to minimize noise during rituals or ceremonies? Did the Egyptians intentionally create this acoustic environment to enhance the perceived sanctity and mystery of the space? The investigations also considered the role of the pyramid's shape. The sloping sides, combined with the irregular internal geometry, created a complex series of reflections and absorptions. Unlike a simple, smooth-walled chamber, the pyramid's design ensured that sound waves wouldn't travel in a predictable path. This chaotic scattering further enhanced the sound, dampening effect and complicated efforts to map the acoustic landscape. Modern research has incorporated advanced computational modeling, simulating the acoustic behavior of the pyramids under various conditions. These simulations corroborate the findings from physical measurements, providing a more detailed understanding of the complex interactions between sound waves and the pyramid's structure. The models demonstrate how even slight variations in block placement or joint design could dramatically alter the acoustic properties of the space. Interestingly, some researchers have suggested that the controlled acoustics of the pyramids were deliberately exploited during ceremonial activities. The muffled soundscapes might have contributed to a sense of reverence and awe, creating an atmosphere conducive to meditation or religious observance. It's plausible that the Egyptians recognized and utilized this inherent acoustic property to enhance the spiritual experience within these monumental structures. The study of the pyramid's acoustics is an ongoing endeavor, with new technologies and methodologies continually refining our understanding. While the exact reasons behind the Egyptians' deliberate manipulation of sound remain partly shrouded in mystery, the evidence increasingly points to a sophisticated understanding of acoustic principles, far beyond what was previously imagined. The Great Pyramids, then, aren't just silent witnesses to history. They are, in a very real sense, sophisticated acoustic marvels, holding secrets within their stone walls, quietly whispering tales of ancient engineering and, perhaps, ancient beliefs. The sheer scale of the pyramids has always provoked a sense of awe, and a significant portion of that feeling stems from the profound symbolic significance woven into their very shape. It wasn't simply a monumental tomb. The pyramid was, in the eyes of the ancient Egyptians, a meticulously crafted embodiment of their understanding of the cosmos, a tangible representation of the journey of the soul, and the enduring principles governing existence. To truly grasp the pyramid's meaning, we need to delve into the ancient Egyptian worldview, a worldview intrinsically linked to the cyclical nature of time, the relationship between the divine and the mortal, and the movement of the sun. The most dominant aspect of this symbolism revolves around the sun god, Ra. Ra wasn't merely a deity. He was the sun, and the pyramid's form is seen as a precise architectural echo of the sun's daily journey across the sky. At dawn, the sun, Ra, was born from the eastern horizon, rising from the darkness, symbolizing rebirth and renewal. The pointed apex of the pyramid, that piercing shaft of stone reaching towards the heavens, mirrored this rising sun, acting as a direct conduit to the divine realm. The Egyptians believed the pharaoh, as the divine ruler on earth, was himself a link between the mortal world and the celestial one, and the pyramid served to facilitate this connection, allowing the pharaoh's spirit to ascend to join Ra in the sun's rising. But the pyramid's symbolism extended far beyond a simple sunrise representation. The pyramid's four sides, perfectly aligned with the cardinal directions north, south, east, and west, weren't coincidental. They represented the four corners of the world, the boundaries of Ma'at, the cosmic order and truth that the Egyptians strove to uphold in all aspects of life. Maintaining this balance between chaos and order was paramount, and the pyramid's precise orientation ensured that the pharaoh's tomb was correctly positioned within the framework of the universe, safeguarding his spirit's passage. Each face of the pyramid was therefore considered a pathway, a physical manifestation of the forces upholding cosmic harmony. Within the pyramid's structure itself, the shape wasn't just a geometrical form, it represented a complex cosmology. The internal chambers, carefully constructed and precisely aligned, mirrored the realms of the gods. The grand gallery, a long, sloping corridor leading to the burial chamber, was particularly significant. Its imposing height and the diminishing light as one progressed upward symbolized the soul's ascent through the darkness of the underworld, towards enlightenment and union with the Creator God. The walls of the Grand Gallery were decorated with intricate carvings of deities and protective spells, further reinforcing the journey and offering guidance to the deceased pharaoh. Consider the base of the pyramid. Unlike many ancient structures which were built upon a level platform, the Great Pyramid was constructed upon a carefully prepared, slightly descending bedrock. This wasn't a simple, practical decision for construction. It was deliberately chosen to represent the primordial mound, Ben, from which the world was believed to have emerged in creation myths. The Ben was a lotus flower shape, and the pyramid's base mirrored this form, anchoring the pharaoh's tomb to the very foundation of creation. The materials used in construction also held symbolic weight. The limestone, quarried from nearby locations, was associated with purity and resilience qualities essential for the pharaoh's eternal existence. The granite, used for key elements like the sarcophagus and some chamber walls, was even more sacred, associated with the primordial waters of creation and further signifying the permanence and unwavering nature of the pharaoh's afterlife. The precision of the pyramid's construction, the near-perfect alignment of its faces, the accuracy of its angles, is no accident. These details weren't simply feats of engineering, they were acts of profound religious devotion. Every stone was placed with deliberate intent, every measurement considered in the context of the cosmic order. The Egyptians believed that the very act of building the pyramid with its focus on achieving perfect symmetry and alignment, was a form of prayer, a tangible expression of their faith. Furthermore, the pyramid's shape facilitated a complex understanding of time. The rising and setting of the sun were fundamental to their religious beliefs, and the pyramid's apex, perpetually pointing towards the sun, served as a constant reminder of this cyclical process, the eternal return of light, life, and rebirth. The pharaoh, aligned with the sun's journey, was thus connected to this fundamental rhythm of the cosmos, destined to participate in the eternal dance of creation and destruction. The pyramid, therefore, was more than just a tomb. It was a cosmic engine, a testament to the profound connection between the earthly and the divine, and a physical manifestation of the ancient Egyptians' enduring hope for immortality. The colossal pyramids of Egypt weren't built by a single, roaring throng of laborers, as sometimes depicted. Their construction was a marvel of logistical coordination, and at the very heart of that intricate operation were the scribes. These individuals, often trained from a young age, were far more than just record keepers. They were the vital nervous system of the pyramid project, responsible for precisely translating the pharaoh's will and the high priest's pronouncements into concrete actions for thousands of workers. Their work extended far beyond simply noting the number of stones moved. The primary role of the scribe, particularly those attached to the overseer of a specific workforce, was the meticulous maintenance of accounts. Each stone, each block of limestone, each piece of timber, everything was cataloged. The system wasn't a simple tally, it was a sophisticated accounting method utilizing a base 10 system, readily understood across the ancient Egyptian world. Each stone was assigned a unique numerical identifier, meticulously recorded in papyrus scrolls. These scrolls, often remarkably well preserved due to the dry climate, detail the origin of the material's quarry location, the name of the stonecutter who extracted it, and even the precise dimensions of the stone itself. This wasn't merely about preventing theft, although that was undoubtedly a concern. It was about guaranteeing the quality and consistency of the materials used, critical for ensuring the structural integrity of such monumental structures. Measurements played a role equally significant to the accounting. The Egyptians possessed a highly developed understanding of geometry and mathematics, predating many modern applications. The scribes were responsible for consistently applying these mathematical principles throughout the entire construction process. They weren't just relying on a single master builder's eye for alignment, they were employing sophisticated surveying techniques. They used tools such as the merket, a sighting instrument similar to a theodolite, the plumb bob, and ropes marked with specific lengths to ensure that every block was placed with astonishing accuracy. The process of checking alignment wasn't a hurried glance. It involved repeated measurements and adjustments, documented in detail on the papyrus scrolls. These scrolls contained not just the final measurements, but also the intermediate calculations, the adjustments made due to variations in the ground, and the corrections implemented by the scribe in response to the surveyor's observations. Furthermore, the scribes oversaw the organization of labor gangs. The workforce was divided into teams, each under the direction of a foreperson, and the scribes recorded the productivity of each team. They tracked the number of hours worked, the amount of stone moved, and any materials consumed. This data wasn't used to harshly punish workers, but to identify areas where efficiency could be improved. If one team was consistently lagging, the scribe would note this discrepancy and relay it to the overseer, allowing for adjustments in training, resource allocation, or perhaps a change in task assignment. Beyond the purely practical aspects of measurement and labor tracking, the scribes held a crucial supervisory role in relation to the religious ceremonies interwoven with the construction process. The building of a pyramid was deeply rooted in Egyptian beliefs about the afterlife, and the scribes were tasked with ensuring that these religious protocols were meticulously followed. They recorded the precise timing of rituals, the offerings made to the gods, and the measurements of the sacred spaces within the pyramid itself, particularly the chambers intended for the pharaoh's burial. The alignment of these chambers with the stars and cardinal directions was paramount, and the scribes were responsible for verifying this alignment through repeated calculations and observations. The scribe's role extended to interpreting the complex symbolic meaning embedded within the pyramid design. While the architects and master builders were responsible for the physical design, the scribes ensured that the dimensions and layout of the pyramid corresponded to the pharaoh's place in the cosmos, as dictated by the religious texts. They would translate the abstract concepts representing the sun's journey, the deceased pharaoh's ascent to the heavens, into concrete architectural specifications. This involved calculating angles, determining the length of corridors, and precisely positioning the entrances to ensure a harmonious relationship between the earthly and the divine. The scribal team was typically led by a senior scribe, often a priest who combined his religious duties with his administrative responsibilities. This individual possessed not only a deep understanding of the religious texts, but also a mastery of mathematics and accounting. He acted as a crucial link between the pharaoh, the high priest, and the workforce, ensuring that everyone was working towards the same goal. The meticulous record-keeping, the precise measurements, and the careful supervision all contributed to a remarkably organized and efficient operation, a testament to the sophisticated administrative capabilities of ancient Egypt. Without the scribes, the pyramids would have remained an unachievable dream, a collection of random stones rather than the enduring monuments that continue to inspire awe and wonder today. The sheer scale of the Great Pyramid of Giza, and indeed many other pyramids across Egypt and beyond, has always provoked a sense of wonder, a feeling of being confronted with a mathematical puzzle. While we readily accept the immense labor involved in moving and placing massive stone blocks, a deeper, more subtle aspect of the pyramid's design has been increasingly scrutinized by modern researchers: the deliberate use of optical illusions and sophisticated geometric manipulation to create visual effects and, potentially, to communicate complex information. It's not simply about stacking stones, it's about manipulating the perception of space. Early observations by travelers and explorers were often dismissed as fanciful. The regular sloping sides, the nearly perfect alignment with cardinal directions, and the consistent angle of the faces seemed, to some, too precise to be mere chance. However, advances in surveying techniques and computer modeling have allowed us to analyze the pyramids with a new level of accuracy, revealing a system of proportions and angles far exceeding what would have been necessary for straightforward structural support. The key lies in understanding how ancient Egyptians were able to create the illusion of greater height and stability, of a structure that seemed to defy gravity and to stretch towards the heavens with a seemingly infinite grace. The fundamental geometric principle at play is based on the concept of forced perspective. This isn't a new phenomenon. Artists have utilized it for centuries to make objects appear larger or more imposing. The basic idea is that parallel lines will appear to converge in the distance, creating an illusion of depth. The pyramid's design leverages this effect dramatically. The base of each pyramid is considerably wider than its apex. This, combined with the gradual narrowing of the sides, creates a powerful visual illusion. As the eye travels upwards along the slope, the sides appear to get closer together, making the pyramid seem taller than it actually is. More than just a simple optical trick, the angles themselves are crucial. The angle of inclination of the faces, approximately 51 degrees and 51 minutes, is remarkably consistent across all the Great Pyramids. This isn't a random choice. It's calculated to maximize the visual effect of the slant, further amplifying the sensation of upward ascent. The precise angle, combined with the increasing width of the base, generates a profound visual impression. It's a deliberate construction that was designed to draw the gaze upwards, reinforcing a symbolic connection to the sun god Ra and the ascent to the afterlife. Furthermore, the internal chambers and corridors within the pyramids are aligned with remarkable precision to these external angles. The passages aren't just functional, they're geometrically integrated into the overall design. The corridors don't simply lead to the burial chamber, they're part of a carefully orchestrated visual journey, guiding the eye along a specific path and enhancing the illusion of immense height. Researchers have hypothesized that the sequence of chambers and passages might have been designed to mirror the stages of a journey, from the earthly realm to the celestial one, reinforced through the manipulation of visual perspective. Sophisticated computer models, simulating the pyramids from various viewing points, have confirmed that the overall effect is remarkably consistent. The models demonstrate that, regardless of where you stand, the pyramid consistently appears to grow taller and more imposing. This wasn't accidental, it was the product of conscious design. The ancient Egyptians weren't simply building a tomb, they were crafting a powerful visual statement. Beyond the overall appearance, there's evidence suggesting a more localized application of forced perspective. Some researchers have examined the placement of stones within the pyramid's walls and corridors, noting subtle deviations in alignment. These deviations, though small, when considered in relation to the overall design, could have been intended to subtly alter the perception of depth and scale within specific areas. This might have been used to create a sense of enclosure or to guide the eye towards particular features. The potential for complex symbolic communication through geometric manipulation is a subject of ongoing debate. While some theories propose that the pyramid's design encoded precise astronomical data or served as a calendar, the extent to which this was consciously intended remains unclear. However, the fact that such a sophisticated understanding of optics and perspective was employed, a level of knowledge requiring advanced surveying skills and geometric understanding, points to a remarkably advanced civilization with a profound engagement with the visual world. The pyramids are, therefore, more than just impressive feats of engineering. They are testament to the Egyptians' keen observation of the natural world and their mastery of manipulating perception. They represent a deep understanding of how the human eye perceives space, a deliberate application of optical illusions to create a lasting and awe-inspiring monument. A stairway to the stars rendered in stone. The ongoing study of these structures continues to reveal new insights into the ingenuity and beliefs of a civilization that continues to captivate and challenge us today. The sheer scale of pyramid construction wasn't merely a feat of engineering. It fundamentally reshaped the lives of the communities that supported it, creating ripples of change that extended far beyond the immediate workforce. The Giza Plateau, and indeed pyramid sites across Egypt, became vibrant, complex economic hubs, far more than simply places where laborers toiled. The demands of building these monumental structures ignited a cascade of shifts in resource management, trade networks, and social organization. Before the pyramids, local settlements around Giza and across regions like Saqqara and Abusir were generally smaller, often focused on farming and modest craft production. Villages were primarily self-sufficient, relying on the local Nile flood for their harvests and exchanging goods within their immediate vicinity. The arrival of the pyramid builders, primarily from across Egypt, Nubians, Syrians, Levantine peoples, and skilled artisans brought in from distant lands transformed this landscape. Suddenly, enormous quantities of materials were needed: millions of limestone blocks, granite from Aswan hundreds of miles to the south, copper for tools, reeds for mortar, and vast quantities of food to feed the thousands involved. This created an unprecedented demand, forcing established systems to adapt and expand. The quarrying operations themselves were massive undertakings. Teams of workers, often organized into specialized gangs, were responsible for extracting the stone. This work wasn't simply about hewing blocks. It involved significant infrastructure. Roads were built, initially rudimentary tracks of packed earth, and later improved with stone paving, connecting the quarries to the construction sites. Skilled masons and surveyors were needed to direct the extraction, ensuring the blocks were cut to precise dimensions. These individuals, and those involved in transporting the stone, often using sleds dragged over lubricated pathways, gained considerable status and skill, and their knowledge became highly valuable. The quarries themselves attracted permanent populations, establishing settlements that grew around the activity, becoming centers of expertise in stone working and transport. Beyond the quarries, the construction sites demanded a highly organized supply chain. Royal granaries, strategically located to minimize transport distances, swelled with grain from the best producing regions of the Nile Valley. Specialized merchants, initially local farmers, were commissioned to procure and distribute these supplies, transforming themselves into powerful figures in the pyramid economy. These merchants didn't just supply food, they also handled the procurement of tools, ropes, and other essential materials, further consolidating their wealth and influence. The logistical complexity coordinating the delivery of goods to thousands of workers, managing storage, and minimizing waste required a level of administrative skill that far exceeded the capabilities of small villages. The impact extended to craft production. The demand for tools, chisels, hammers, saws, and copper implements spurred the growth of metalworking workshops. Skilled artisans, many of them itinerant, were brought in to manufacture and repair these tools, and to produce specialized items such as ropes and baskets. The need for finely crafted furniture and decorative items for the elite overseeing the construction also stimulated woodworking and jewelry production. New industries emerged, fueled entirely by the Pyramid Project, and established artisans found new markets for their products. Perhaps the most profound change was the shift in social hierarchy. While the pharaoh and his immediate court retained ultimate authority, the Pyramid Project created a complex network of intermediaries, overseers, scribes, merchants, and skilled artisans who wielded considerable power and wealth. These individuals, often drawn from outside the traditional Egyptian elite, gained influence through their control of resources and their involvement in the administration of the project. The construction process demanded a degree of centralized control, but it also fostered a vibrant marketplace of skills and resources, creating opportunities for social mobility and ambition. The rise of these new, powerful figures challenged the traditional social order, introducing a fluidity that was previously absent in Egyptian society. Furthermore, the construction created a sense of collective purpose and shared identity. The thousands of workers involved, not just those directly engaged in quarrying and building, but also those providing support services, were united by a common goal: to honor the pharaoh and ensure his passage to the afterlife. This shared commitment fostered a sense of belonging and loyalty, and it contributed to the stability of the kingdom during a period of significant upheaval. The legacy of the pyramid construction extended beyond the immediate period of building. The skills and technologies developed during this time, particularly in quarrying, transport, and organization were later applied to other projects, such as the construction of temples and palaces. The economic and social changes introduced by the pyramids laid the foundation for the centralized state that would emerge in the Old Kingdom, fundamentally altering the course of Egyptian civilization. The site of the pyramids, therefore, isn't just a reminder of ancient engineering. It's a testament to a period of extraordinary transformation, a period where a nation's ambition reshaped its society and its future. The desert sun, a warm amber glow, casts long shadows across the Giza Plateau. But tonight, the focus isn't on the pyramids themselves, but on what lies hidden beneath their massive forms. For centuries, the secrets of the pyramids have been teased out through careful observation, painstaking excavation, and educated guesswork. However, a revolution has been brewing, a quiet, persistent advance driven by the development and application of incredibly sophisticated geophysical surveying techniques. These aren't the days of simply brushing away sand. Instead, scientists are now listening to the very bones of the Earth, interpreting subtle vibrations, and mapping the underground structures with a precision previously unimaginable. The core of this new approach relies on a diverse toolkit of technologies. Ground-penetrating radar, or GPR, is perhaps the most commonly employed. Essentially, GPR sends out short pulses of radio waves into the ground. When these waves encounter a change in density, a rock layer, a wall, a buried chamber, they reflect back. The GPR unit then detects these reflections and translates them into a detailed image, much like a sonar system used to map the ocean floor. The data generated by GPR provides a virtual slice of the ground beneath, revealing the shape, size, and composition of objects buried below. Newer, more advanced GPR systems utilize frequency sweeps, allowing researchers to distinguish between different materials with greater accuracy. For example, a change in the speed of the radio waves returning will indicate a dense stone, while a slower return suggests a less dense material like mud brick. But GPR is just one piece of the puzzle. Magnetometers are also playing a crucial role. These devices measure variations in the Earth's magnetic field. The construction of the pyramids involved the use of copper and bronze tools, and the smelting of metals created localized magnetic anomalies. By mapping these anomalies, researchers can identify the locations of workshops, storage areas, and even the precise routes of the tools used during construction. Some recent surveys have revealed networks of magnetic signatures stretching for hundreds of meters, suggesting a far more complex and organized logistical operation than previously understood. Another powerful technology is electrical resistivity tomography. This method utilizes electrodes to send electrical currents into the ground. Different materials offer varying resistance to the flow of electricity. Consequently, the strength of the returning current is indicative of the material's properties. This technique is particularly effective in identifying the presence of mortar and brick, which often have different electrical conductivity than the surrounding stone. In the Saqqara Pyramid Complex, for example, resistivity surveys have identified what appear to be extensive subterranean corridors and chambers associated with the step pyramid. The precise purpose of these structures remains a subject of intense investigation, but the geophysical data provides compelling evidence of a sophisticated, interconnected network. Recent research is extending beyond the immediate vicinity of the pyramids to explore the wider regional context. Seismic surveys, utilizing controlled vibrations, are mapping the geological structure beneath the entire Giza Plateau. These surveys are revealing the underlying faults and rock formations that influence the choice of site and the stability of the structures. Surprisingly, researchers have discovered evidence of substantial subsidence, sinking of the land in the area surrounding the pyramids, a process that likely contributed to the deterioration of some of the older tombs. Understanding this subsidence is vital for conservation efforts, ensuring that future excavations and monitoring don't inadvertently destabilize the remaining structures. Furthermore, the rise of drone-based lidars, light detection and ranging technology, is dramatically changing the landscape of pyramid research. LiDAR utilizes laser pulses to create highly detailed 3D maps of the surface, even through dense vegetation. When combined with aerial photography, this technology provides unprecedented views of the pyramid complexes, revealing previously obscured features and allowing for incredibly accurate measurements. Recent lidar surveys have identified numerous smaller structures and anomalies that were missed by traditional surveying methods, suggesting a much denser and more complicated settlement pattern around the pyramids than previously imagined. Perhaps the most exciting development is the integration of all these data streams. Scientists are no longer analyzing each technology in isolation. They are combining the information from GPR, magnetometers, LiDAR, and seismic surveys to build a comprehensive, three-dimensional model of the subsurface. This integrated approach allows for a far more nuanced understanding of the construction process, the layout of the complexes, and the environmental factors that shaped their evolution. The data is being processed using sophisticated computer algorithms, allowing researchers to identify patterns and correlations that would be impossible to detect manually. This isn't just about finding new chambers. It's about understanding how the pyramids were built, why they were built that way, and the complex interplay between the builders, the environment, and the enduring legacy of these magnificent structures. The investigations are ongoing, with each new survey promising to unveil further secrets, pushing the boundaries of our knowledge about one of the greatest architectural achievements in human history. The Earth itself is whispering its stories, and scientists are finally learning to listen. Let the echoes of the ancient stones settle within you. If these videos brought a little peace, consider subscribing and sharing them with those who seek quiet moments. As we leave the majesty of the pyramids behind, allow your mind to unfurl, like a ribbon in the twilight, calm and unhurried, until sleep arrives.